Okay, I'm going to do a next example. Try to set it up the way that I had it before. So we're always going to put the PDE here. This is an example, this is the fifth example in the notes. I'm picking it after the existence and uniqueness theorem for a particular reason. So we have x times the t derivative of u minus t times the x derivative of u is equal to 0, and we have u is equal to f on the x-axis. And then we will give our parameterization for gamma here, which is just going to be x naught 0 for x naught running through the real numbers, and then we'll have our three different equations: x prime of s, t prime of s, z prime of s, and then our initial conditions: x of 0, t of 0, z of 0. Those are the things, that setup we will have for every single problem we do here. X prime is whatever is multiplying the x derivative, so that is minus t. T prime is whatever is multiplying the x derivative, so that is x. And then z prime is going to be to the right-hand side, that's 0. X of 0 corresponds to that point, that's x naught. This is 0, corresponds to that point. And z of 0 is just u, whatever that is, evaluated at this point, that's just f of x naught. Now, there is a particular reason related to the fact that this is coming after the existence and uniqueness theorem that I'm not telling you what f is, so we'll talk about that in a minute. In other words, I'm not, the other example that said f of x is equal to 1 plus x or whatever, I don't have that explicitly here. Okay, so let's go through solving our equations. Now, you'll note here, this is the first time where our system is not, where our system is not decoupled. In other words, our system is coupled. Meaning, if I look at these two equations here, x prime depends on t and t depends on x. So there are several ways that we can solve this differential equation. It's a system of first order differential equations. You can do the matrix eigenvalue eigenvector method. That's perfectly fine. I'm going to do something a little bit different. I'm going to look at this equation, and I'm going to say if I take the derivative of this equation, I get x double prime is equal to minus t prime. If I just differentiate that, I get x double prime is equal to minus t prime, but t prime is equal to x. So this is equal to minus x. So in other words, this becomes x double prime plus x equals 0. Now I know this has solution. Remember, s is the variable. This has solution. X of s is equal to a cosine s plus b sine s. The characteristic polynomial is r squared plus 1, so the roots are plus and minus I, so this is the form. Now I know that t is equal to minus x. So t of s is equal to minus, I think I said minus x, but it's minus x prime. Okay, if I take the derivative of this, I'm going to get minus, so it's going to be a sine s minus b cosine s. So now, of course, I need to figure out what a and b are, and I'm going to use my initial condition for that. So x of 0 is equal to 0. So 0 is equal, sorry, not 0. X of 0 is equal to x naught. This is x of 0. If I plug in 0 to this equation here, I get a cosine of 0, which is 1, plus 0, sine of 0, 0. So this says a is equal to x naught, and then I have 0 is equal to t of 0. Well, this is t right here. I know that a is equal to x naught, so this is going to be x naught times 0, so I don't need to worry about that, and then minus b. So it says 0 is equal to minus b. In other words, b is equal to 0. Okay, so a is equal to x naught, b is equal to 0. So this gives me the following: x of s A is equal to x naught, b is equal to 0, so x of s is equal to a cosine s. T of s, a is equal to x naught, b is equal to 0, is just going to be equal to, sorry, I had an a there, with the x naught. T of s is going to be equal to x naught sine s. So x is equal to x naught cosine s, T of s is equal to x naught sine s. Z of s is constant. Z prime is 0, so Z of s is constant. So Z of s is just going to be equal to f of x naught. Okay, so now let's sketch some characteristics. So let's say this is the x-axis, this is the t-axis. Let's look at a generic x naught here. Okay, so what do we get? We've got x is equal to x naught cosine, t is equal to x naught sine. So what this is the parameterization of a circle of radius x naught that goes through the origin. So I'm going to have this circle. This is a circle, or not that goes through the origin, but is centered at the origin. So I'm going to have something like this. Okay, that's a circle, and so it passes over here at minus x naught. It's not a good circle, even for like sketching. Okay, so this is x naught. All right, this is minus x naught. Okay, and so what do we know? We know that f is constant on each of these characteristics. We know on this circle, u is equal to f of x naught. So if I take a generic point here, so there might be alarm bells going off for some of you. There should be. I'll talk about it in just a moment. For this generic point, xt, u of xt is going to be equal to f of the square root of x squared plus t squared. Because this circle is a circle of radius x naught, the radius of the circle is the distance from there to there, which is the square root of x squared plus t squared. Okay, and so now the question is, does this satisfy the PDE? Does it satisfy the problem over here? Well, I'll let you think about whether or not it satisfies the PDE, but let's look at u of x0. So u of x0 is equal to f of the square root of x squared. Now, what is the square root of x squared? It is not x, it is the absolute value of x. And so this is f of the absolute value of x. Okay, well now we're starting to see some problems here. So geometrically, look at what's going on here. I have a characteristic that starts at this x naught and traces around over to this x naught and intersects the curve gamma twice. This is a problem because I have my point xt here. I'm solving for x naught. In terms of the picture, I picked that x naught to solve for, but I just as easily could have solved for that x naught. But what if f of x naught is not equal to minus f of x naught? Then there's going to be a problem here. So what's going on here? Well, the issue, there's a couple of things that are happening here. One is that there's going to be a problem when x and t are equal to 0 because we're going to have the b vector is going to be equal to 0, or the b component of the vector is 0. This is 0. So this line is non-characteristic, or sorry, this line is not non-characteristic because the tangent vector there is going to be equal to 0. And that's going to, if you think back to the 2x2 matrix that I had right over here, that's going to result in a matrix that is singular. There's a problem there. The other problem is this sort of highlights some of the local idea about the existence and uniqueness theorem. So I can have a solution over here, for x greater than 0, I'm going to have a solution that works just fine. If I look at x less than 0, I'm going to have a solution that works just fine. The issue comes as I cross through this point here. So I can make this work. I can essentially make this work if I impose some condition on f. For example, f of x naught equals f of minus x naught In other words, if I impose the condition that f is even, then this function right here is going to be a global solution to this equation with a problem at 0 regarding differentiability, but otherwise it'll be a solution. Okay, so notice here's an example. Look, this is a linear differential equation. The left-hand side is linear, the right-hand side is 0. This isn't even a semi-linear equation, just a very easy linear equation. And we already have a case where like this existence and uniqueness is not working in the way that we might expect it to work. For linear equations based on our previous experience with linear equations for ODEs. So remember, in ODE land, when we looked at the theory of ODEs, if we have a linear equation, then the solutions exist and are unique globally. Here we have a linear equation, and that's not what is happening at all here. Okay, that's it for this video. I hope you think through some of this on your own.